All right, let's take a look at our Unit 3 review. So we go back to reviewing complex numbers at the beginning of our unit. It says to simplify and write your answer in the form of a plus bi. So standard form complex number, a plus bi, where a and b are real numbers. So remember, a complex number is a number formed by adding multiples of I. I is our imaginary number in math. And let's make a note about what we know about the number I. So I, defined as the square root of -1, which implies I squared equals -1. Right? If you square a square root, you get rid of it. So again, that's something we like to use in helping us simplify higher powers of I. So just remember, I squared equals -1. We can use that to simplify. Right? Anytime we have an exponent of 2 or more, we need to reduce or simplify the imaginary number. And our first problem, in problem number 1, is asking us to add two complex numbers together, two numbers of the form a plus bi. So to do that, we're going to add up, right, the like terms. So -7 plus 11, for example, we know that adds up to 4. We know the -5i. All right, we got to add that to 3i. So we end up getting what? 4, right, minus 2i as we add those together. So again, find the sum, right, of those two complex numbers. Right? So let's look on. Let's go ahead and look at our next example. And this is, again, is standard form. Let's go ahead and talk about a and b before we move on. A being the real part of the complex number, which is 4. B is the imaginary part, the coefficient of your imaginary number. All right, so next example, we want to subtract the two complex numbers. So as we do that, we get -10 plus 14i. We need to go ahead and distribute, right, that minus sign through. So we have a -7 and a minus, which becomes a plus 3i. Be careful with that as you distribute to both parts of that complex number. And then we add up our like terms. So we got a -17. We've got a 14i. We have a 3i. They add up to 17i. So in the end, we end up with a difference of -17 plus 17i as our standard form complex number. So again, our real part and our imaginary part. All right, let's go to finding the product of two complex numbers. As we're looking at the product, we're going to need to distribute, right? And doing the product here. All right, so let's go ahead and look at that. So finding our product, 7 minus 2i times 2 plus 6i. Well, we need to distribute. So let's go ahead and begin. Distribute the 7 through. 7 times 2 is 14. 7 times 6 is 42i. And then we'll go ahead and distribute the -2 through, or -2i, I should say. -2i times 2 is -4i. -2i times 6i is -12. I squared. I times I is I squared. Now, got to simplify now. So like terms, we have a couple of I terms that we need to combine. So we have 14 plus 38i minus 12. Now, what do we know about I squared? I squared equals -1. So that's minus 12 times -1. So we have 14 plus 38i plus 12. Right? As we add those together, we get 26. 14 and 12 add up to 26. So I have 26 plus 38i as our product, these two complex numbers in standard form there. So again, be careful as you work in those. Again, distributing, combining like terms, reducing, using your properties with complex numbers. So we've done an example of addition, subtraction, multiplication. Let's do division. So dividing complex numbers. Now in dividing a complex number, our first step is to focus in on the denominator. We want to eliminate I altogether. And to do that, we need to multiply by the conjugate. And conjugate, of course, is the opposite. Conjugate of denominator. So again, the opposite. So what is the opposite of negative 3 minus 7i? It's negative 3 plus 7i. So as we multiply by the conjugate, we would have to do the exact same thing with the numerator. So we've got to multiply by a fraction of 1, so it doesn't change our number that we're looking at. So again, we're good to go. As long as we do the same thing with the numerator and denominator as far as multiplying goes. So again, that's the same thing as multiplying by 1, so it doesn't change anything. But here's what we like about that. Multiplying by the conjugate will eliminate I altogether. So I want to go ahead and do that. So we're looking at, again, finding the product of 1 plus I times negative 3 plus 7i over, and let's put that, we'll put it in that same color. Let's go ahead and put that in blue, just so you see that is what I introduced. There's something new in this problem. Let's go back to our colors here. So again, negative 3 plus 7i in the numerator. And then in the denominators, we're looking at negative 3 minus 7i. I'm going to multiply it by the conjugate, which is negative 3 plus 7i. So let's go ahead and do that together. Let's distribute. So again, we multiply 1 times negative 3, 1 times 7i. So we get a negative 3. We get a plus 7i. And then we need to distribute. We need to multiply the I through. I times negative 3 is negative 3i. I times 7i is 7i squared. All right, and in the denominator, let's go ahead and do our product. Now, when we're multiplying by complex conjugate, we're going to be eliminating I altogether. There's a shortcut we've talked about in our lecture. The product of complex conjugates always simplifies down to the square of A plus the square of B. So it should be negative 3 squared plus negative 7 squared, which is 9 plus 49, or 58. In the end, we should get a product of 58. But let's show that. We don't have to use any shortcuts. We can go ahead and multiply and show our work. Negative 3 times negative 3 is 9. Negative 3 times 7i is negative 21i. And now let's go ahead and take the negative 7i and distribute it through. So negative 7i times negative 3 is a positive 21i. Negative 7i times 7i is negative 49i squared. And again, we need to start simplifying what we have. Now keep in mind, we know I squared simplifies to negative 1. Right? I is defined as the square root of negative 1, so I squared would equal negative 1. As we're combining like terms, well, we've got our 7i minus 3i, so I got negative 3 plus 4i plus 7 times negative 1, all divided by, now the denominator, what ends up canceling out? The I terms are opposites. That's why we multiply by the conjugate. So we end up simplifying to 9 minus 49 times I squared, or 9 minus 49 times negative 1. So simplifying that down, we got negative 3 plus 4i minus 7 divided by 9 plus 49. And there's that property of a squared plus b squared, right? 3 squared plus 7 squared, or negative 3 squared plus negative 7 squared. Now, as we go with that, we got a couple of constants to combine. Negative 3 and negative 7 make negative 10. So we got negative 10 plus 4i divided by 58. And what I want to do is make it look a little bit better. Let's go ahead and break this up and divide out the common factors that come into play. So what is negative 10 over 58? Well, we can divide out the common factor of 2, right? We can divide a 2 into both. So we can go ahead and reduce these two fractions. As we do that, we do negative 10 divided by negative 2, that's negative 5. 58 divided by 2 is 29. And 4 over 58 reduces to 2 over 29. All right, so there it is. All right, there's our simplified complex number, a plus bi. So that's showing you the work behind dividing complex numbers. Right, as we're dividing, we're going to multiply by the conjugate of the denominator. Now again, you can, if you want, you've got your calculator and you can check these. Your calculator does have your imaginary number on there. So you could, if you want, pull up your TI. All right, and above the decimal key, you'll see I. So if you want to do this problem, for example, let's put in our problem we just did, 1 plus I divided by negative 3 minus 7i. Now be careful, we need the denominator in parentheses. Make sure it reads both terms in the denominator. So more than one term, make sure you group it. And you get the enter button. Now it'll give you a complex number in standard form back, but it gives you an ugly decimal. It gives you these irrational numbers here. Now let's go ahead and convert these back to fractions by hitting the math key on the left hand side, and you can see command 1 says fraction. So that'll take and convert back to fraction form with those decimals. And as you hit the enter button, you will get what? You will get negative 5/29 plus 2/29 I. And I'll let you do that on your TI. Mine will not allow me to do that on my application one. But use your math fraction command and you can get back to this standard form, a complex number that we just found. All right, so again, that's working with complex numbers. Now let's look at simplifying some higher powers of I. So moving on down here to problems 5 through 8. It says simplify I to the 34th power. All right, well what I want to do to simplify is I want to use what we know about I squared. I squared equals negative 1. All right, so this is the same thing as saying I squared. Let's rewrite it using I squared. I squared to what power? And if you remember, I'm going to show the property. A power raised to a power means you multiply the exponents. A to the x times y. So this would be equal to what? I squared. 2 times what's 34? 2 times 17 is 34. So now we can reduce because we know what I squared equals. That's negative 1. And we know that negative 1 to any odd power is going to simplify to negative 1. So yeah, I to the 34th power is equal to negative 1. And we got there quickly just using properties of exponents and our definition of what I squared equals. Again, power to a power, multiply the exponents. So again, I'll make that note here. This is multiply the exponents when you're raising a power to a power. So a little review back to exponent properties. Well, anytime you're dealing with an even power on I, it's going to reduce to either negative 1 or positive 1. So let's do the same thing with I to the 12th power. Well, I to the 12th power is I squared raised to the 6th power because 2 times 6 is 12. Well, that's equal to what? Negative 1, because I squared equals negative 1. And negative 1 to the 6th power, well, since we have an even power, any even power on a negative base makes it positive. So, yeah, negative 1 to the 6th power would be a positive 1. So, I to the 12th power equals 1. All right, now it's a little different when you have odd exponents. All right, with odd powers, all right, like we have in this example, factor out an I. So factor out an I will be your first step. So let's do that. So for example, I to the 13th power. If we factor out an I, we're left with 12 of them. That'll be I times I to the 12th. Yeah, I times I to the 12th, still I to the 13th power. But now we can reduce I to the 12th power. So let's go ahead and do that. we know that at even power, we can use I squared as the base, right? We just did I to the 12th power. It's 2 times 6. So this is equal to I times what? Negative 1 to the 6th power. And again, negative 1 to the 6th power is positive 1. 1 times I is I. So it simplifies down to, right, I. And that's true. With odd powers, it's going to always equal I or negative I. All right, so let's go to our last example in this set. All right, in this next example, we're looking at 2i raised to the 7th power. All right, well, this time they've changed it up a little bit in that we have a coefficient. We have a couple factors here in our base. Well, the first thing I'm going to do is go ahead and apply the power rule and distribute my power to both factors. So as we do that, this is equal to 2 to the 7th times I to the 7th. And then we can go ahead and reduce 2 to the 7th power. That's 128. We multiply 2 together 7 times, 2 times 2 times 2. We're going to get 128. Now I to the 7th, we need to reduce. And since this is a odd power, we need to use our factoring property. We got to make it even before we can use I squared as far as the exponent goes. So if you factor out an I, what do you get? You get I to the 6th power left. So I times I to the 6th, still I to the 7th. But we like that because now I can reduce I to the 6th power using I squared. So we have that even power of 6. We know that 2 times 3 is 6. So as we're reducing down, I got 128 times I squared, which is negative 1 cubed. Right? I squared to the 6th power is negative 1 to the 3rd power. And we got 128 times what? Times I times negative 1, which is 128 times negative I, which equals negative 128 I. So there's 2i to the 7th power, right, with our imaginary numbers. So that's a review back to beginning. We're dealing with complex numbers. And the reason we define complex numbers, right, numbers formed by adding multiples of I, is because we can work with complex numbers when we deal with quadratic equations. Quadratic equations have the possibility of complex number solutions, which you get into in your next 2 examples on your review. In solving quadratics, you can have up to 2 real number solutions, 2 complex number solutions, or even 1 real number solution. So looking at solving algebraically quadratic equations. So let's take a look at this first example. You can use any method you like. Solve using any preferred method. Now in this one, I've already got it in standard form. Remember, in a quadratic equation, standard form is we have our x squared term, our x term, and our constant term all on one side equals 0. If not, that would be my first step. Get everything on one side, set it equals 0. A is what we refer to as coefficient of x squared, B is what we refer to as coefficient of x, and C is our constant. Well, I always try to factor. If I can factor, I can get to my solutions quickly. Every quadratic has 2 linear factors. We don't always see them because they're not always nice integer factors, but this one is. Let's go ahead and build them. We know we need an x and x up front for x squared term. And our goal in factoring is going to our constant term and finding a factor combination. Well, 13 is a prime number, and that means its only factors are 1 in itself, but thankfully those work. If I do a minus 13 and minus 1, right, the outer and inner product, right, we would check it, and that's negative 1x, that's negative 13x. They would add up to that middle term, negative 14. That's our goal. The outer and inner product got to combine the middle term. So there are your 2 linear factors. Yeah, if you distribute that, you're going to get x squared minus 14x plus 13 back. And with that, now that we have a factorization, right, we use our linear factorization property. We go use our 0 factor property. So we're ready for our 0 factor property. And with our zero factor property, we know if this product's going to be 0, then one of these factors must equal 0. So x minus 13 could equal 0, or x minus 1 could equal 0. As I solve for x, I get x equal to 13, or x equal to 1. Right, as we move those constant terms over, use the addition property equality. We can add it quickly over to show our work here. But with that said, what do we come up with? We come up with two different real number solutions. And now you can check them, right? You plug them in, graph it, check your work. Right? And they both do check. And you plug in 1, for example. 1 squared is 1, 1 minus 14 is times 1 is 1 minus 14, which is negative 13. Negative 13 plus 13 is 0. And same thing happens when you plug in 13, substitute. Now here's the thing, we were able to factor on that one. If you look at this next example, you can't factor. You say, well, what are your two linear factors for this quadratic? Yeah, we can put x and x up front, but there's no factors of 9. They're going to work together, right, to make the middle term coefficient. All right, can't factor. Doesn't have those integer solutions. So we have two other methods that we can use to solve a quadratic like this one, where we can't factor, where we don't see those solutions. We don't have those nice integer or rational values for solutions. All right, where we might have irrational or complex number solutions. In this example here, that you're going to need to either resort to completing a square or using your quadratic formula. Now I will show you both methods, and you can choose. Alright, I'm going to do the complete the square method first. Alright, completing the square method says to group your x terms on one side by themselves. So you move your constant term over to the other side. You would add the 9 over. So you group the x terms on one side, and we can make a note of that step. Group x terms. Alright, now to create the square, we take half of b. As long as your coefficient of x squared is 1. Now if it's not 1, make it 1. Divide it out. Get rid of it. So if it's 1, which it is here in this example, identify b. So b is equal to 4. So we're going to take half of that number. So as we take half of 4, we get 2. So half of b squared, alright, we need to add in on both sides of this equation. We've got to add the same number on both sides to keep it equal. But we're adding half of b squared so we can create a square in this quadratic trinomial. And then we can solve using square roots. So now we have x squared plus bx plus half of b squared. X squared plus 4x plus 2 squared. Well, that's the same exact thing as saying x plus half of b. X plus 2. All raised to the second power. So x plus 2 squared is the same thing as saying x squared plus 4x plus 4. So I'm creating my square. And this is equal to 9 plus 4, which is, what, 13? So I got x plus 2 squared equal to 13. And then we go ahead and get to x. As we create a square, we can take the square root of both sides. Just be careful. Make sure you remember that even roots can be positive or negative. So doing that leaves me now with square root of x plus 2 squared, which is x plus 2, equal to plus or minus square root of 13. And we solve that for x. We go ahead and subtract the 2 over to the other side of the equation. And we come up with our solution of x equal to negative 2 plus or minus square root of 13. So I've got two different real number solutions, right? And you can separate them if you like. Sometimes they'll ask you to separate by a comma. Right? You can separate them either way. This is negative 2 plus, again, the square root of 13. Right? Or x equal to negative 2 minus square root of 13. So there are two different real number solutions. Now that's completing the square. Now a lot of people will use the quadratic formula. So I'll show you both ways. All right, now quadratic formula is this. X equals negative b plus or minus square root of b squared minus 4ac, all divided by 2a. So you have a formula. You got your formula, plug in your numbers, get your solutions. So what is a, b, and c? So in this example, right, we had what? X squared plus 4x minus 9 equals 0. So we can talk about a, b, and c. So a is 1, right? There's a, there's b, and there's c. So there's our values of a, b, and c. So x is equal to, as long as it's equal to 0, you've got everything ready to identify. Negative b, so negative, the coefficient of x we'll call b, negative 4. Coefficient of x is 4. Plus or minus b squared, so that's 4 squared, minus 4ac. 4 times 1 times negative 9, all divided by 2 times 1. There's our solution set. We've got it. The only thing with quadratic formula is you got to simplify. That's where your work comes in. So we got to make this look better. We need to get down to negative 2 plus or minus square root of 13. We've already solved it with creating a square, so we should be able to find that. 4 squared 16, minus 4 times 1, negative 4. Negative 4 times negative 9 is plus 36, all divided by 2. And we got negative 4 plus or minus square root was 16 plus 36. That's 52, all divided by 2. Now keep in mind, square root of 52, irrational number. Right? Let's go ahead and break that up. That has a perfect square factor. Right? We know that 4 is a factor of 52. I know that 4 times 13 is 52, and we all know the square root of 4 equals 2. So this is equal to the square root of 4 times square root of 13, which is 2 square root of 13. So as you go back to your solution set, negative 4 plus or minus 2 square roots of 13 over 2. So again, we'll plug that back in to our problem. Now as we simplify, my last step, let's go ahead and divide out the common factor of 2, right, that shows up in both terms. Right, negative 4 over 2 is negative 2. 2's divide out, and here's our solution set. So that's with quadratic formula. So you see both methods. You got your complete square method, and you got your quadratic formula. Most people probably prefer quadratic formula. So you can see again your solutions. Let's do it one more example. Let's do number 11. All right, now number 11, your first steps, we need to set it equal to 0. We need to get this in standard form. So we need to move these terms over. So we need to subtract the 12. We need to minus the 5x over to the other side. So go ahead and do that. Go ahead and move everything over to one side of the equation. So as we do that, what do we end up with? We got x squared minus 5x minus 12 equals 0. So moving those terms over to the other side of the equation. All right, now if you want, use your quadratic formula. So we got a, b, and c. So again, let's talk about quad formula. Let's go use it. Quadratic formula. So a, again, let's identify all these numbers. There's a, there's b, there's c. So as we plug it in, we'll have our solution set. So x is equal to negative b, so negative 5, plus or minus square root of b squared, negative 5 squared, minus 4ac, 4 times 1 times negative 12, all divided by 2 times 1. There's your solution set. Let's simplify. Negative 5 is positive 5, plus or minus square root negative 5 squared is 25, minus 4 times a times c, minus 4 times 1 is negative 4, negative 4 times 12 is what? Positive 48. All right, so we got a plus 48 here, all divided by 2. So we end up with 5 plus or minus the square root. As we add those together, we get 73, all divided by 2. So here's your solution set. We got 5 halves plus or minus Now, square root of 73 has no perfect square factors. You can't rationalize that root like we did with square root of 52. It doesn't have a perfect square factor of 4 or 9 or 16. All right, so that's as simple as we get it, no common factors. But there's our solution set, 2 different real number solutions. So in all 3 of these problems, we ended up with real number solutions. But again, keep in mind, you can have complex number solutions. We have a negative inside the square root, which means we have I. We can define our complex number. So that's quadratics. So we'll stop there and take a break, and then we'll look at graphing a quadratic in our next problem.